the Birch reaction in the last class, and this is a dissolving metal reaction, and the mechanism is very similar to the dissolving metal reaction when we reduce our triple bond to a trans double bond. And again, just like in that mechanism, we went through a radical anion intermediate, where we have a compound that has both a radical and an anion, and that radical and that anion want to be as far away apart as possible. So that particular intermediate is what dictates that our double bonds are going to be opposite from each other in the final product. This intermediate also dictates where the double bonds are going to be if we have any R groups attached to the benzene ring when we start the reaction. So this negative charge is going to really affect where the double bonds are going to be, depending on what we start with. So if we start with an R group that's electron donating, and an electron donating group can donate electron density away from itself through induction. Again, we're thinking about the fact that we have a radical anion intermediate. Would an electron donating group be more or less stable, closer to a negative charge? It's donating electron density, so if it's closer to a negative charge, is that more or less stable? Less stable. Why? What's the rule in this class? What's the main thing for everything that you should be looking back at? Positive and negative charges attract, like charges repel. So electrons are negative. If a group is donating electron density, donating negative charge to a negative charge, that's going to repel. That's unstable. The basics of this whole class is that positive and negative charges attract and like charges repel. So based on that, electron donating groups are going to destabilize the negative charge. So the most stable intermediate is going to be one where the R group is not next to the negative charge. So this is not observed, and this is why. These are our two possible intermediates. If the reduction occurs at this carbon, then we'll have the negative charge by that electron donating group, and that's super unstable because, again, electrons are repelling each other. Our electron donating group is donating electron density to a negative charge, and that's not stable. So if the reduction does not occur at that R group, then the negative charge is further away, and remember, inductive effects get less the further away from the group occurs. So since this is further away, this is our more stable intermediate, so we only observe the product where the reduction is not occurring at the electron donating group carbon. And then the other double bond has to be opposite from the first because our lone pair has to be opposite from our radical. Conversely, if we have an electron withdrawing group, that's going to stabilize the negative charge. Electron withdrawing groups pull electron density towards it, therefore making the negative charge more stable. So when we have an electron withdrawing group, we have an electronegative atom here. It's pulling electron density towards itself. Then we have reduction occurring at that carbon because our most stable intermediate will be one where the electron withdrawing group is closest to the negative charge because it's going to stabilize it the most. So electron donating groups, we don't have reduction at that carbon, but electron withdrawing groups, we do have reduction at that carbon because, again, don't memorize this, think about the intermediate. Electron withdrawing groups stabilize the negative charge, so the closer it is to the negative charge, the more stable. And it's all about what's going to be our lowest energy transition state. And again, that radical anion is determining the fact that our double bonds are opposite from each other, and it also dictates where the double bonds are going to be, if there's an R group attached. So let's look at this example. We have the benzene ring, that's where the reduction's occurring. So what we have to do is look at all the groups attached. Don't be confused because this is in a ring, it's irrelevant. the fact that these two carbons are attached doesn't matter. So we're going to look at the direct attachments at each of the carbons of the benzene ring. So we need to determine if we have electron donating or electron withdrawing groups. Our carbon-oxygen double bond is an electron withdrawing group, and this is an R group directly attached to the ring, so this is an electron donating group. So we have two groups attached to the benzene ring, and they're going to dictate where the double bonds are going to be. So if this is an electron withdrawing group, we're going to get reduction at this carbon because that lone pair is going to be most stable being close to the electron withdrawing group. But because this is an electron donating group, that means that we can't have reduction at this carbon because the negative charge would be more unstable closer to that group. Again, the fact that this is a ring is irrelevant. You're looking at what's directly attached. So it wouldn't make any difference if this was an ethyl group that wasn't attached or not. So this carbon will be reduced, that's next to our electron withdrawing group, but the carbon that's next to our electron donating group will not. So now we have to draw our possible products that agree with this, but still have our two double bonds opposite from each other in the final product. Because they have to be opposite from each other for it to be that radical anion. So in this case, this is our only possible product where our two double bonds are opposite from each other. This carbon is not reduced, so it's still at that double bond, and this carbon is. Sometimes there will be two different ways that this can happen, but in this case, this is our only possible product where we're in agreement with what the electron donating and electron withdrawing groups are going to do, and also our two double bonds are opposite from each other. If we look at this one, we have an ethyl group, and that is an electron withdrawing group, so we will not get the reduction there. So first off, C and D, well, C and D are incorrect. We have a different amount of carbons in C and D. We are not, ethyl groups are not a good leaving group. We're not doing anything to break a carbon-carbon bond. C and D don't make any sense anyway. But A and B, we do have reductions, and A is the correct one because we are not getting the reduction at that carbon. And also, B is incorrect because not only will we not expect the reduction of this carbon, but our double bonds are going to be opposite from each other in the ring, so our radical and our anion could be as far away apart as possible. If we look at this example, here, again, we're looking at the same thing, but we have an electron donating group. And NO2, remember, looks like this. This is what our NO2 group always looks like. It always has a positive charge on the nitrogen and a negative charge on one of the oxygens. So, remember, our lone pair wants to be near a positive charge because that's going to stabilize it. They are attracted to each other. So our NO2 group is a really strong electron withdrawing group. Very strong because it can pull electron density really close to it because of that nitrogen being a positive charge. So based on that, this is an electron donating group, and we will not see reduction, but here we have an electron withdrawing group. So we will see reduction at that carbon. So we're going to get reduction at that carbon, but we're not going to get reduction where the isopropyl group is attached. So the possible products that we see, well, first off, C, we don't have our two double bonds opposite from each other. So that's not going to be the correct answer no matter what the R groups are. The two double bonds have to be opposite from each other in the Birch reduction because of the radical anion. Again, here is our intermediate that is dictating all of this. So C isn't right no matter what. If we look at B, we will get the reduction at this carbon, and that's not shown. And also we will not get the reduction at this carbon. So B is not correct. In A, we are not getting the reduction at that carbon, so that's okay. But we should get reduction here, and that's not reduced. So that's still not the right answer. D is our possibility where we are not getting reduction at that carbon, but we are getting reduction at that carbon, and we're still getting the two double bonds being opposite from each other. So D is our correct answer. Do not get confused with where the double bonds are starting in the ring, because remember, it's irrelevant. All of these carbons are participating in the double bond. So oftentimes, if it helps, you can redraw this ring with this circlet, which represents the double bonds between all of the carbons. And we also have the resonance structure where the double bonds are between the opposite ones. So don't let that confuse you. That's not dictating anything. The double bonds are always between all the carbons in the benzene ring. Just a little bit about large structures that have multiple benzene rings. One example would be graphite. Graphite is layers of sheets that have fused benzene rings. You don't have to count all the pi electrons, but it's fused of a bunch of benzene rings. So overall, the total structure of graphite is aromatic. It's a very strong structure. It can donate electrons really easily. The problem is it's often not very soluble because it's a bunch of carbons that are nonpolar. So it's not soluble in water, so that's an issue. We can make it more water soluble by putting functional groups that make it more water soluble, but oftentimes that will contribute to it being less available to have electron density and therefore be an electronic. Graphite's really strong. They have a couple of papers right now that have come out where they're taking graphite derivatives and feeding it to spiders, which then spin really, really, really strong silk. But don't worry, when they stop feeding it to spiders, they no longer have that strong silk, so if they get out, they're not going to be doing this really, really strong silk everywhere. At least that's what they claim. But it's really cool that they've been feeding it to spiders and they're getting this really strong material. Kind of a melding of polymer chemistry and using what nature can do. Yes?
How do the graphite sheets bond or fuse together? Is it some type of limited distance?
Well, this is a covalent bonds.
Right.
But as far as different sheets,
yes.
So the different sheets are coming together by what we call pi-pi stacking, and it's sort of like an intermolecular force. So what we have is a bunch of rings that have these unhybridized p orbitals. And if the rings, so all of the carbons in the graphite sheet have these unhybridized p orbitals. So if the ring is flat, that means the p orbitals are facing up and down. So when another sheet comes over, the p orbitals that are facing up and down of one sheet can interact with the p orbitals facing up and down of the other sheet, and they can actually donate electron density from one sheet to the other based on what we call pi-pi stacking. So this pi-pi stacking is great, except it also contributes to the fact that they're not very soluble in water, because you can't get the water molecules, or even not just water, they're not very soluble in a lot of solvents, even non-polar solvents, because to dissolve, the solvent has to get between the different molecules and start breaking them up, and the pi-pi stacking is so strong. So that's been one of the issues with using things like graphite, is solubility. Overall, they're just not very soluble. And if you're trying to get it in an electronic, you have to dissolve it in something, usually, to get it then to make a film of it. So that's a really interesting, and this is sort of a subset of polymer chemistry, so I know a little bit more about it. Another example of these big benzene-containing molecules is a buckyball. It's called C60. It's basically a big sphere of benzene rings and 5-membered rings, and it looks like a big soccer ball when you draw the whole thing. It is overall aromatic, which you might wonder, how can it be if it's a ball? How can it be overall aromatic, because then it's not planar? And the answer is, even though it's not overall flat, the surface area is so big because, again, this is 60 carbons, that it's just like the Earth. You can stand here and you feel like it's flat because it's so big because of the circumference. So we see this in the molecular scale of the buckyballs, that it still retains its aromaticity even though it's not an actual flat molecule. But it has to do with the surface area. Another one is a nanotube, or you might hear these called carbon nanotubes. Again, these are big tubes of benzene rings, and they have been used in electronics and things like those sort of applications. Again, the issue with them is often solubility, but you can, and we're going to talk in the next couple of, the next chapter, reactions that we can have of the benzene ring and still retain aromaticity, which is going to be our electrophilic aromatic substitution reactions. So you can put more water-soluble groups or soluble groups on here, but it does affect its ability to transfer electrons. But they have been used in conductive plastics, meaning plastics that conduct electricity, energy storage, adhesives that conduct electricity, thermal materials, fibers and fabrics, catalyst support, and biomedical applications. But one of the big problems is solubility, again, with these. So they're pretty cool, and they've been used a lot in applications. You can look up, we have the ability for almost all ACS journals. So if you go on the ACS journal website and just look up nanotubes, you'll find some articles on how they've been used and what you're being researched for. And you have full access to those if you look them up while you're on campus or signed in through the library or proxy service. So we pay a lot of money for you to have the ability to look up American Chemical Society journals. So you can do that. So speaking of which, how do you take a big aromatic compound and react it and still retain the aromaticity, but then get functional groups on it? And that's what we're going to be talking about in the next chapter. Aromatic substitution reactions. Reactions that retain our aromaticity. The reactions we looked at before in the previous chapter have been either reacting groups outside of the ring or reducing the ring somehow. But here we want to retain the aromatic ring completely. Now, some of these reactions can be done with other aromatic rings, but for this particular chapter, we're going to focus on benzene because it's our more common aromatic compound and what is used the most in drugs and pharmaceuticals and applications. So that's what we're going to be really focusing on, is the benzene ring. Though in theory, a lot of what we're talking about will also work with other aromatic systems. In lab, we do ferrocene, which is a 5-membered aromatic system, and they can still work there. We're going to talk about electrophilic aromatic substitutions, but we're also going to talk about nucleophilic aromatic substitutions and one other reaction that also will retain the ring. So we already know how we can do an addition reaction with a double bond in cyclohexane. And we can add Br2 and we'll add 2 bromines across the double bond. They're going to be anti. We've learned all of this. And this is why it's really important that when you draw these structures, you do draw the double bonds. Because the reactivity of cyclohexene versus the reactivity of benzene is completely different. We can take Br2 and react it with benzene as much as we want, and we will not get a reaction. Because our aromatic compounds are a lot different than our non-aromatic compounds. And this is definitely a non-aromatic compound. It doesn't have a closed loop cyclic ring system. So it's very important, and I will mark it wrong, if your answer is supposed to be benzene and you draw anything that's not benzene. Just because it's a 6-membered ring does not make it benzene. However, if we take this reaction and we add something like iron, we can actually get a reaction to occur. Now, if you look at this reaction, what kind of process is it? Because we know this is an addition. But what is happening here? How would you describe that process? Is it an addition? We retained a pi bond. So it doesn't look like it's an overall addition. What actually looks like is happening? What's the difference between our starting material and our final product? It looks like it's substituting. It looks like bromine substituting for what? Hydrogen. A hydrogen side of it that you group. So this can't be just a simple SN2 reaction when bromine is substituting hydrogen. And it's not. And even if that was happening, iron wouldn't really make sense there anyway. So there's more that's going on than just a simple substitution. But overall, this process is a substitution. But it's not just a simple SN1, SN2 that we've talked about. So overall, we are substituting hydrogen with bromine, but more is going on with that mechanism. And what is it about iron that allows a reaction to occur when we could have heated up Br2 and benzene as much as we want and we won't get a reaction? So that's the other thing we're going to look at. So this is actually what we call an electrophilic aromatic substitution, and we're going to break down that name. We can do similar reactions with bromine if we add something like iron. We can also do this with chlorine, NO2, SO3H. We can actually add an R group, or we can add an acyl group, or aceto-O group. And we're going to look at all of those reactions and what reagents take to do that. But overall, it's the same process. We're substituting a hydrogen with some group. So the name comes from the fact that we have an aromatic ring, so hence the aromatic part. The overall process is a substitution. But the first part is really important, electrophilic. Electrophilic is saying that the ring is going to attack an electrophile. And that's where the iron comes in when we mix it with Br. It's going to make our bromine a very good electrophile. So if we think about the ring acting as a nucleophile, what does that mean? If our benzene ring is acting as a nucleophile, what's the definition of a nucleophile? Subtracted positive charge. But what does it do? What is the actual process? When a nucleophile attacks, how do we describe what happens to the electrons? It's donating electrons. So with the benzene ring, where is its available electrons to donate? Does it have a lone pair? No. The pi bonds. So if the benzene ring donates the electrons as a pi bond, what does that do to one of the pi bonds? Is our final product going to have a pi bond? No. This does, but I'm just talking about if it's acting as a nucleophile. It's going to give up its electrons from the pi bond, and its intermediate is no longer going to have a pi bond. So if we attack an electrophile, our intermediate is going to look like this. Is this system aromatic? No. We now have an sp3 carbon. So this intermediate is going to be really high. That means, depending on the electrophile, that activation energy is going to be really high. So for this to act as a nucleophile, what does this electrophile have to be? As far as strength is concerned. Would this happen with a weak electrophile? No. Will this happen with a moderate electrophile? No. This will only happen if the electrophile is strong. And that's why, even though Br2 is a okay electrophile and it works well with other pi bonds, it does not work with benzene ring, because the benzene ring is not a good nucleophile. It can be a nucleophile under the right conditions because it does have electrons in an outer p orbital, but it's not a good nucleophile. So if we have something that's a really, really weak nucleophile, we want it to react with an electrophile, we need a very, very strong electrophile. All of our reagents are going to make the groups that the benzene ring is attacking strong electrophiles. If they're not strong electrophiles, this reaction won't occur. So hence, electrophilic aromatic substitution. It has to be a strong electrophile for this reaction to happen, or no reaction is going to occur, no matter how much heat you put into it. So the aromatic protons are replaced by an electrophile, and our ring is acting as a nucleophile. That's three. What's going on? Okay. So since our aromatic ring is acting as a nucleophile, we need a very, very strong electrophile because our resulting product, our resulting intermediate, is no longer aromatic. And a typical double bond, that's not relevant. We're not forming a compound that's no longer aromatic. So what we need is a very strong electrophile. Br2 is good enough electrophile with a normal pi bond. A normal pi bond is an okay nucleophile. Still not a great nucleophile, like a carbon with a negative charge, but an okay nucleophile. So our Br2 is what we call polarizable, and Br is a good leaving group, so the other Br can accept electrons. But there's no overall polarity because the two bromines are bonded together and they have the same electronegativity. So while bromine can give a pretty high induced partial positive and partial negative charge because the bromine can stabilize the negative charge very well because it's big, it's still not a very, very strong electrophile. At least not enough to react with the benzene ring. So what we need to do is make it a better electrophile. Now we can do that by reacting it with iron. Now typically what we use is FeBr3, not just elemental iron. And if we did take elemental iron and react it with a bunch of Br2, we'd eventually form FeBr3 because it's our stable form when iron's in the presence of bromine. But we typically use FeBr3. Technically you can use AlCl3, but usually what we do is keep the halogens consistent so we don't have weird byproducts. So if we're using Br2, we'll use FeBr3 as our reagent, and this is a Lewis acid, not a Bronsted-Lowry acid because there's no proton transfer. It's a Lewis acid. The iron is accepting electrons. So when our iron accepts electrons, we're going to form this structure, which our bromine, because here in this structure our bromine has negative charge, will typically break that bond to form Br+, and then our FeBr4 with a negative charge. This is super unstable, so it's a very, very good electrophile. Very strong electrophile because now we formed a bromine with a positive charge. It really wants some electrons. So now even a weak nucleophile can attack this, and that's what we're going to see with our benzene ring. So that's why this reaction doesn't occur without our Lewis acid present, because our Br2 is not electrophilic enough. Now that we have a really reactive electrophile, this is just what we talked about. Now we have a really reactive electrophile. And this is really the difference between here and here is kind of a sort of a resonance structure. Not really a full resonance structure, but sort of. At any given point, you have this bond and this. It's more an equilibrium between these two. And you can draw it either like this or like this. Even like this is a strong electrophile. So you can think about it both ways. So once we form this really strong electrophile, our benzene ring can attack, and that's going to put our bromine on. Now notice our hydrogen is still intact, and it's going to be intact because hydrogen is not a good leaving group. In a typical substitution reaction, our thing that was substituting is our nucleophile, but here our bromine's acting as the electrophile. Now we're going to form this resonance stabilized positive charge, though it is no longer aromatic. So this positive charge has resonance structures, And here's our free resonance structures. And this is what we call the sigma complex, and it's going to be really important once we have R groups, any substituents attached to the benzene. Right now, we're just going to focus on the reaction of putting the bromine on an unsubstituted benzene, but later on, these resonance structures are going to be really important, and we're going to really dissect them. Notice, because our benzene ring is acting as a nucleophile, our intermediate is a carbocation, and that's really important. You will have to draw these mechanisms, and you should be able to draw a good sigma complex, and we'll be using them to explain our regioselectivity. But right now, benzene doesn't have any regioselectivity because there's no other functional groups. Later on in the chapter, we're going to be focusing on that. Now, the last step in the mechanism is going to be the reformation of the aromatic ring. So how do we do that? Well, it's very simple. We still have a bunch of bromine floating around, which can act as a base. So it will deprotonate the hydrogen and reform the benzene ring. So this isn't like any other substitution reaction in that we're not having a nucleophile attack the ring and a leaving group leave. But the overall process is a substitution. But it doesn't look like SN1 or SN2. So this is an electrical aromatic substitution mechanism. Now notice, technically, our bromine can act as a nucleophile and attack the carbocation instead of deprotonating. So the question is, why doesn't that happen? Why the substitution rather than the addition of the second amount of bromine? And the answer to that is really simple if we look at the difference in the stability of the products. If the addition occurs once we have that carbocation, then we don't have aromaticity. If the elimination happens, where we deprotonate the hydrogen and form our double bond, then we regain our aromaticity. Our aromaticity is going to be lower in energy, so therefore the substitution product is our thermodynamic product. And in fact, our thermodynamic product is usually a little bit lower in energy than our starting material, whereas our addition product is higher in energy. So the addition product is actually non-spontaneous. It's not going to be favored, so we won't get any of that. So we're always going to get the substitution product because we reform the aromaticity. Again, this activation energy is dependent on how unstable, how reactive our electrophile is. So the stronger the electrophile, the higher we're starting our starting material in energy, and therefore the lower the activation energy. So we have to have a very strong electrophile to make the ring act as a nucleophile. It's not going to do it on its own. We can also do this with Cl2. It's the same basic mechanism. The only difference is typically we use AlCl3. We use aluminum because aluminum is a better fitted size for chlorine than iron is. That's the only reason. It's still going to do the same thing, which is make our chlorine a really, really good electrophile. It's typical that if you're wanting to add chlorine, if chlorine is what you're wanting to put on the ring, then you're going to use AlCl3, because technically you can use FeBr3, but there's a chance that you'll get bromine in your final product. So just stay consistent with your halogens. If you're using iron, if you're using bromine, you use FeBr3. If you're using chlorine, then you'd use AlCl3. So those are the most common. Now in lab, we even do this reaction with iodine, which can work as well, but we don't look at it as much in this chapter. So again, the same basic mechanism. We are forming HCl because of that last step, the elimination step. So the chlorine can attack and we form a very unstable Cl positive, which the ring can then attack, and you form the sigma complex just the same. Fluorination is generally too violent to be practical. Iodination is often too slow and you don't have good yields, but vanillin that we're using in the lab has functional groups that's electron donating, so it makes the reaction possible. But typical benzene that has no functionality is usually too slow with iodine. And we're not going to look at thermodynamics and dissect it like we've done in the past, but basically it's just not going to give you a low enough negative exothermic or endothermic exergonic reaction. But fluorination, it will work, but it's really violent, so it's not practical. Too reactive. So again, this is your general mechanism. We form a very strong electrophile, which are our benzene ring attacks. We have our sigma complex, which has the resonance stabilized positive charge, and then we reform the aromaticity by a deprotonation. So one thing to note about this general mechanism, the electrophilic aromatic substitution must occur at a carbon that has a hydrogen. If the carbon does not have the hydrogen, we can't do this last step of deprotonation and reforming the double bond. So if there's another R group there and it's not a hydrogen, then it cannot happen at that position, because the group that is the electrophile is substituting is not a leaving group. It has to be a hydrogen because we have to be able to remove it with a base. So notice that about the mechanism. The other thing to notice is, and we're going to be getting to this not today but later in the chapter. Today we're going to talk about other reactions. The other thing to notice is that our sigma complex is a carbocation, so you should already recognize that a positive charge is stabilized by electron donating groups and destabilized by electron withdrawing groups. So that's going to bring us to looking at our regioselectivity and our rate of our reaction later on in the chapter. So anytime we have a positive charge is stabilized by electron donating groups. It wants electrons, so groups that will donate electrons is going to make it more stable. But electron withdrawing groups that's trying to pull density away from the positive charge, well, the positive charge doesn't have electron density. So if you're pulling more density away, it makes it more unstable. So those are two things to notice about the mechanism that we're going to be looking at later in the chapter in a lot of detail. So when we look at this one, our answer is going to be B. We're going to substitute in one position. Regiochemistry at this point is irrelevant because our benzene ring has no R groups, nothing attached, no substituents. This is not possible. If we did get two additions, we would not retain the benzene ring. So this is our only possibility. Bless you. Besides halogens, we can also do this reaction to add what we call sulfonation. Here we're going to use fuming H2SO4, and we're going to talk about what that is and what that means. It's not exactly what it just sounds like. Fuming H2SO4 means something to a chemist, so we'll talk about what that means. But if we use fuming H2SO4, then we're going to add SO3H2 ring. Now don't put SO4H because that's not stable. That sulfur would have a charge. It's SO3H. So we're going to look at that mechanism. And something about the fact that we're using fuming H2SO4 is going to make that sulfur very electrophilic. Because the benzene ring is attacking the sulfur. Notice the bond is between carbon and sulfur. That's also important when you draw this product. I don't want to see OSO3H. The bond is not between oxygen and carbon. It's between sulfur and carbon. That's really important. So what is fuming H2SO4? So fuming H2SO4, fuming means that not only do you have sulfuric acid, but you also have SO3 gas. So SO3 gas is where the fuming is. It's never written SO3 gas, H2SO4. It's always written fuming H2SO4. I won't mind if you write SO3, H2SO4, because that's what fuming means. But you need to recognize it because if you're going to take something like the MCAT or anything like that, they're going to use the term fuming, which is common. So basically, you're pumping in SO3 gas over H2SO4. SO3 is really, really electrophilic. Well, it's pretty electrophilic. We're going to make it more electrophilic with H2SO4. We have a sulfur. This is what SO3 gas looks like. And we have a good deal of positive charge. Remember, sulfur, we will look at sulfur a little bit in chapter 14. Sulfur can have an expanded octet. It's lower. Look, we have a periodic table now. It's lower on the periodic table than oxygen, so it can't have an expanded octet. It can't have more than the electrons. Yeah, we can't put one on this wall because there's more than one. But we have one on that wall. So we see sulfur as an expanded octet. So we can have that resonance structure, though. Remember, this isn't our most contributing resonance structure. Our most contributing resonance structure is the one where sulfur only has 8 electrons. but in that resonance structure, sulfur has a positive charge. So we have a lot of positive charge at that sulfur. If we look at an electron density map, it's really blue. And remember, blue means a place of less electrons. Red means more electrons. So more of the electron density is centered on the outside. So we have some electrophilicity at that sulfur. Also, typically a double bond, carbon-carbon double bond, even carbon-oxygen double bond, we have really good overlap of non-hybridized p orbitals because carbon and carbon are the same size. Carbon and oxygen are roughly the same size. They both have the same over quantum number because they're in the same room. But oxygen and sulfur don't have good overlap, which means that we don't have a very strong double bond between them. Sulfur is under oxygen in the periodic table. It has a larger quantum number, and therefore the p orbital is bigger because this is a 3p orbital, whereas this is a 2p orbital. So that 3 means we're at that higher energy level, and it's going to be bigger. So we don't have as good of overlap. So that's another thing that makes this double bond not as strong as a normal carbon-carbon or carbon-oxygen double bond, or even carbon-nitrogen, because those are all around the same size. We all have the same outer energy level. So it's not very effective because of the size mismatch. We have an inefficient mismatch. As a result, our SO behaves a bit more like a single bond, so we say it has a lot of single bond character. So the S atom in SO3 carries a good deal of positive charge. It's not a very stable double bond, so it acts more like a single bond. The aromatic ring is stable, but it also has electrons. So what we can do is attach this pretty strong electrophile. When it attacks SO3, the result is the carbocation is resonance stabilized. Now notice our oxygen does have a negative charge. That's where that H2SO4 is going to be important. So we still have the same basic resonance structure. And we're going to talk about SO3H, whether it is an electron withdrawing group or electron donating group later on in the chapter. Right now we're just focusing on this reaction. So notice this is the same mechanism as before. Our electrophile in this case, instead of chlorine or iodine, is an SO3 negative. So that's what we see. Again, notice the bond is between carbon and sulfur. So that's very important when you draw that product that you represent it that way. You don't have to draw out 3 oxygen bonds, but what you do have to draw out and be specific is that the bond is between carbon and sulfur. Sulfur is then bonded to the oxygens. So again, we have the same sort of resonance structure. We again will have a deprotonation to form our final product. The only difference with this mechanism is we will have a proton transfer to make this oxygen a neutral charge. That's where the H comes from. It's coming from our H2SO4 acid. So the H2SO4 acid is really to do that step. Also, our conjugate base of H2SO4 or any water that's present is usually H2SO4 has some water present can deprotonate. But this last step is the only difference between the other mechanisms and this one. And that's just because we're not going to isolate the negatively charged oxygen. So what we have is, and you don't necessarily have to draw this out, you can. But the big thing is the bond is between carbon and sulfur. Otherwise the mechanism is the same. So fuming is in the SO3 group. And your answer is SO3H is in your group attached. H2SO4 is not the electrophile. The electrophile is the SO3 gas. The nice thing about this reaction, and we're going to use it later in the chapter, and we're going to exploit this, is that it's really easy to remove. So chlorine, iodine, not easy to remove, but the SO3H is. If we use concentrated fuming H2SO4, meaning we use a lot of SO3 group, then we get the FAR reaction to occur. However, if we use dilute H2SO4 with no SO3 present, then we can remove it and reform the carbon-hydrogen bond. Which means this reaction is highly reversible, and later in the chapter, we're going to utilize this as a blocking group to block certain positions. And that's really what it's mostly used for. Typically, the purpose of using SO3H to add it onto our ring is not going to be as a final product. It's typically going to be to put on, block this area, and then remove it. So we're going to exploit the fact that it's highly reversible. The next one we're going to talk about is reacting with HNO3. So a mixture of sulfuric acid and nitric acid will cause the ring to undergo nitration, and we're going to put a NO2 group on it. Again, the bond is between carbon and nitrogen, not carbon and oxygen. So you need to represent that when you write it. I don't want to see O2N written. I want it to be specific that the bond is between carbon and nitrogen. And we're going to look at the mechanism. So this doesn't work well with this HNO3. We actually have to have the acid present for the electrophilic aromatic substitution to occur. So what happens is our NO3 group will react with one of the hydrogens of H2SO4 because H2SO4 is a strong acid. So we have some available electrons and we get this product. Now typically we won't have 3 charges on a product, but again this is a very strong acid, and also the NO2 group always has those 2 charges, so you kind of consider it overall neutral. It's special. Once we get that, we have a good leaving group in water. So what will form is the nitronium ion, and this is what's highly electrophilic, the nitrogen with that positive charge. It can accept the electrons really well. It's going to have to push the electrons onto the oxygen, and then we form NO2. So we need the H2SO4 with our HNO3 to form this nitronium ion, which means you're not putting a 1 and a 2 here. Those 2 things have to react before the reaction can occur. You typically will take your benzene ring and then throw in HNO3 and H2SO4 together because they need to react to form this. HNO3 itself will not react with the benzene ring. We have to form that nitronium ion. Otherwise, it's not a strong enough electrophile. So the nitronium ion is very unstable, and it's going to be a really strong electrophile, so our benzene ring attacks. Again, same basic mechanism, no different than the other ones. So our electrophile now is the positively charged nitrogen. We form our NO2 group. Again, the NO2 group always has a positive nitrogen and a negative oxygen. That's its stable group, so we don't have to do anything to change that. So our last step is, of course, a deprotonation, typically by a little bit of water. That's the byproduct. Also, you could show the conjugate base of H2SO4 deprotonating, but that's less likely because H2SO4 is super stable. So it's more likely that the water formed in this step is going to deprotonate. That still forms H3O+, so something is deprotonating in the mechanism. And that's going to happen because forming the benzene ring is the most stable. The NO2 group is really useful because we can then take the NO2 group and we can reduce it with zinc or iron, or in our case in the lab, tin, NHCO, to form NH2. And later on that's going to be really, really useful to us. So sometimes you might see the reaction combined, that we're reacting with HNO3 and H2SO4. That puts on the NO2 group, followed by zinc and HCl, which reduces it. And that's a really useful reaction. And later on, we're going to talk about why that's a really useful reaction and why we exploit it. So right now, we're not really going to focus on that. So looking at this, and we're going to come back to it as well and look at the mechanism later when we talk about why it's useful. But it's not really useful. Right now, we're just talking about how to put an NH2. Now, there's no way to directly put an NH2 group on because NH2 is not an electrophile. So we have to use the very electrophilic HNO3 H2SO4 reaction, and then we can reduce it. And this is a reduction. The reduction is happening at the nitrogen. So you should be able to calculate the oxidation state of nitrogen when it's in O2 and the oxidation state of nitrogen when it's in H2, and you will see that we have a lowering of oxidation state. So this is a reduction, but we're describing the nitrogen as opposed to a carbon, like in other oxidations we've discussed in reductions. So if we look at this one, we react HNO3 and H2SO4, we're going to form the NO2 group. And of course, we're retaining the ring because we do so in all of these reactions. Now we're going to talk about putting on a carbon bond and also some limitations with that. So, you might think if we have an alkyl halide, we may just get a substitution reaction to occur. But alkyl halides react as electrophiles, but they're not very strong electrophiles. So we need some sort of catalyst to make the alkyl halide a good electrophile. Again, for the same reason why Br2 doesn't react with our double bond. Even though our double bond is somewhat nucleophilic, this carbon, even though it's decently electrophilic if we have a strong nucleophile, it's not electrophilic enough for this to occur. So just like in our electrophilic aromatic substitution of the halogens, we need a Lewis acid to make it a good electrophile. So we need to make it a strong electrophile. What we'll typically use, if our leaving group is chlorine, we'll typically use AlCl3. If it's bromine, we'll use FeBr3 again. Again, just to stay consistent with when halogens are in the reaction mixture. But again, we need to have a good electrophile. So we do that with using a Lewis acid catalyst. And it's going to catalyze the reaction. We do reform AlCl3 again. And then we can get a new carbon-carbon bond where our electrophile is double bond and the nucleophile is a double bond and our electrophile is the carbon. So let's look at what that looks like and why the Lewis acid helps make it be a really strong electrophile. So again, just like with the Br2 or Cl2, the chlorine can attack our aluminum. But now instead of having a Cl-Cl bond, we have a carbon-Cl bond. So that's the only difference. So then again, we can get a good leaving group and we form a carbocation. A carbocation is a great electrophile. It's very unstable. So we can then get the attack by the nucleophilic ring. So we get the attack, and eventually we're going to form our sigma complexes. It'll have all of its resonance structures. I'm skipping the resonance structures right now, but you know that the carbocation is resonance stabilized. And then a base will come in, likely another chlorine atom, and deprotonate to reform our ring. So what we form is an alkylation. A new carbon-carbon bond, a new alkyl group is added. Now there is a pretty big limitation to this, and you should recognize it pretty easily, and it's the fact that we're going through a carbocation intermediate. What's our limitation with our carbocation? What's our most stable carbocation? It's our most stable carbocation. Looked at this a lot. Tertiary. What's our least stable carbocation? Primary. What happens every time we have a carbocation rearrangement reaction that we have to look out for? Just like we always have to look out for rearrangements. So that is a limitation with this reaction, is that we can get carbocation rearrangements once we form this carbocation, which can lead to a product that we don't. Another problem with this reaction is it's pretty electrophilic, but there's really no way to make this carbocation more electrophilic. So this reaction doesn't occur if there's any electron withdrawing groups on the ring, because it's just not electrophilic enough. So we have that limitation as well. If we look at this one, C is going to be our answer. That's very straightforward. We're going to form, when we react with AlCl3, this carbocation, and that's where we're going to attack its secondary. However, if we start with a primary alkyl halide, we don't get very much of this. Now notice we do still get some, because even though a primary carbocation is really unstable, under these conditions we can force it to form because of butylose acid. But as soon as it forms, we're going to get the rearrangement, and our major product is going to be from the rearrangement. So just like every reaction we've talked about so far, if there's a carbocation and a rearrangement is possible, it will occur, and that will lead to our major product, which means getting the addition at the primary position is unlikely. So we're going to talk about how to fix that, but of course we're going to get that shift. So the answer to this one is we would get the rearrangement product as our major, which is the more stable tertiary carbocation. Just like any time you're going through a carbocation. So we will continue this and talk about acylation on Friday. Y'all have a great day.
You did back test yet?
No, I haven't graded it yet.
Okay.
You too.